Hi, everyone. This is Chip Shearer from the University of New Mexico, and I just want to welcome you all to the Survey CASA Moon Planetary Sample Science Seminar today. And we're really fortunate to have Tony Gargano from the LPI, NASA JSC, and UNM CSI giving a presentation on his work on stable isotopes on lunar materials. And the title for his talk is the Stable Isotope Composition of Volatile Elements on the Moon, Characterizing the Isotopic Effects of Planetary Devolatilization. And Tony, go ahead, it's all yours.
Great spot. All right, good morning, everyone. Thank you for coming. As Chip said, my name is Tony Gargano, a postdoc at the LPI and NASA JSC, as well as UNM CSI. And I'm excited today to give the talk in CASA Moon. My title is very broad, and I wanted to begin by reiterating what Yang Liu said last week about how the Apollo samples are a gift that keeps on giving. And ever since the return, they've been used as type specimens to compare other planetary materials to. And that's kind of what I want to focus on today is broadly what we've learned by looking at the stable isotope values of different elements, different rocks, and some of the nuances of what that tells us about how planetary bodies retain or lose volatile elements. And this helps us understand how the myriad of processes that occur throughout planetary evolution kind of affect the volatile inventory of planetary bodies. And if I can progress the slide, there we are. Now, whenever I make one of these talks, I really enjoy going back in the archive to find some cool images, some feel-good photography from the Apollo era. And I want to begin by kind of establishing how our view of lunar materials has changed a lot since the Apollo era. And ever since kind of the preliminary examinations now, broad scale, we've seen a depletion in many volatile elements in lunar igneous rocks relative to similar terrestrial analogs, as well as an overall kind of absence of hydrous minerals. Now, in the modern era, we've measured almost the entire periodic table of stable isotopes in lunar materials. And the rationale for this is that lunar materials have experienced kind of extreme processes, extreme manifestations of natural phenomena. So they're great type specimens to compare, to characterize any given process. Now, I don't need to belabor this point in this group here, but this wide range of volatile element stable isotope values have been attributed to several stages of lunar evolution. It was very tumultuous and high energy, meaning that many of these processes can be attributed to several stages of the moon's evolution. So ranging from the fractionation of precursor materials, such as that in Theia, to occurring from the giant impact, so the dynamics related to vaporization and condensation of the proto-lunar disk, and dynamics related to how that vapor and melt move between the two bodies. And entire talks to be given on any given element and the isotope system in these processes. What I'm focusing on today are these latter three. And specifically, I want to look in depth at the rock analogs we have to test the relative effects of these latter processes. So ranging from the degassing of the magma ocean to later volcanic degassing during Mare volcanism, and then lastly, what I've been looking into a lot the past couple of years of impacts and space weathering phenomena. Now, I want to by no means suggest we have definitive conclusions for a lot of these processes, but really I want to discuss what our group has been looking at specifically and provide kind of a nuanced take of what these measurements mean and try to understand what processes are actually driving the boat here in terms of why the moon is isotopically anomalous in many respects. So here are the rock suites we're talking about today. These include the Highland suite, an intrusive plutonic rock suite that are some of the oldest rocks we have in the moon. These characterize early crust building processes, as well as late-stage magma ocean crystallization, as well as kind of a difficult to withstand effect of impact processing. We also have the Mare basalt suite, including the volcanic glass beads. These represent volcanic processes, as well as recording the effects of magma ocean degassing in their source regions. And we can also test the effect of different eruption styles and how volatile elements are lost from volcanic rocks. And lastly, the impact rocks broadly. These rocks more specifically show the influences of the impact process itself, as well as the mixing of impactor material into lunar materials. So I'm going to quickly go through volcanic rocks here in terms of Mare basalts, and specifically look at this question whether or not the fractionation was occurring largely from the magma ocean degassing, or from later Mare volcanism. Now, there are two dominant rock suites, the high and low TI Mare basalts, and their age differences we can use to test whether or not the source regions for these rocks retain distinct volatile element stable isotope values. Now, in terms of the specific processes that we can attribute to have caused the anomalous stable isotope values of lunar materials, there are several distinct physiochemical conditions that we need to consider when looking at lunar volcanism. And when I first started grad school, the state of the research was really kind of an in-depth questioning of some of these basic parameters that may influence the degassing pathways of these rocks. So parameters like pressure and chemical speciation can really change how a system can evolve when it loses volatiles. And in terms of the physiochemical condition of the moon, it's very distinct relative to the Earth, where the effective vacuum at the lunar surface has been thought to have at least made devolatilization more efficient, and perhaps isotopic fractionation flowing from it more extreme. Additionally, the redox state of lunar magmas are significantly more reducing than the Earth, and this results in remarkably different chemical speciations of volatile elements during degassing. In the case of chlorine and zinc here, they're very different. And while I'll not be going into great depth to these processes, we have tested them by experiments or by comparison in one way or another to try to come up with the most robust conclusions we can. And ultimately, these combined processes of pressure and chemical speciation can be broadly attributed to why lunar volcanic rocks are devolatilized in different ways than terrestrial rocks. Now, for the next slide, I'll be presenting some of our work published a couple of years ago with James Dutton and Alex Halliday, where we measured the exact same rock suite for combined chlorine, zinc, and sulfur isotope values to be able to compare these together and see what is actually happening to these rocks when they're exhumed and degassed. Here I'm showing you a plot of the combined zinc, sulfur, and chlorine isotope values of Mare basalts. And we're going to discuss this in more detail as we go further on, but as a first brush approach, I want to convey the fact that we see no distinction between these isotope systems in the low and high TI Mare basalts, despite the fact that they're different ages. So the fact that they have indistinguishable stable isotope values, we largely relate this to a source region inherited signature, meaning that these compositions that are different from the Earth relate to affecting the giant impact, with minimal influence from post-eruptive degassing, specifically in terms of the effusively erupted rocks. Now, we can spend a lot of time on these data, but really what I want to discuss in more detail is the outliers here and what is driving their variability. And I think this question is best discussed in terms of a Rayleigh distillation model. And what these models describe are the isotopic evolution of a system undergoing the loss of a fractionated component, such as a vapor. And you'll see two lines in this plot here. The red line describes the residual component, and the blue line represents the vapor being driven off that residue. And there's two acronyms, SBC and WSC. These stand for water-soluble chloride and structurally bound chloride. And the chlorine isotope system is particularly powerful for this test because we're able to isolate and measure that vapor component of that water-soluble chloride. And when we look at the data for Mare basalts here, when we separate the water-soluble and structurally bound chloride for these rocks, we can see that they're isotopically distinct here. And the lower water-soluble chlorine isotope values are direct evidence for post-eruptive fractionation. However, when we look at the relative magnitudes of the volatile contents in the water-soluble relative to the insoluble phase, we see that most of the chlorine exists as the water-soluble phase. And what this relates to is an inefficient loss of volatiles from effusive post-eruptive crystallization. And really what I want to move on next here is the comparison of the volcanic glass beads. The volcanic glass beads are really important, and generally they're thought to be more petrogenetically primitive in this sense, while still being related to the Mare basalt source regions. And the volcanic glass beads are distinct in the fact that they have rather high soluble chloride contents and high isotope values, and this is representative of a generally larger isotopic fractionation and more extensive depletion of volatile elements occurring during explosive volcanism. And this larger fractionation is most evident in terms of sulfur isotope values. Well, I'm behind one slide. That's why I'm a bit behind here. There we go. This larger fractionation occurring during explosive eruptions is most evident in terms of sulfur isotope values. And on the bottom plots here, you're seeing the sulfur isotope values of volcanic glass beads compared to Mare basalts and melt inclusions within glass beads. And when we make this comparison, we can see that we have a more significant loss of volatiles in the volcanic glass beads, as well as the sulfur isotope values range between 0 and -15 per mil. And the sulfur isotope values gives us a lot of constraints in terms of the physiochemical condition of the system. And here we go here. This very large amount of sulfur loss contributes to, is resulting from how the eruption style occurred, where the glass beads are formed by a very fragmented magma that had a very high gas phase volume present there. And this very high gas phase volume means that we have a large partitioning of volatiles into that gas phase relative to the melt. So in the case of sulfur, we have a very large loss of sulfur to the vapor phase relative to fluorine and chlorine. And when we model the effects of this effect in terms of sulfur isotope values here, relative to this saturation vapor pressure, this P over P sat value in the upper right, the P over P sat of 0 is effectively a pure kinetic degassing regime where you have degassing into a vacuum, whereas P over P sat of 1 means that you're having an equilibrium fractionation of sulfur in this case. So the sulfur isotope compositions of these glass beads gives us direct evidence for a near quantitative equilibrium loss of sulfur to the gas phase when these magmas were erupted. Now, another critical facet to understand here in terms of the glass beads is that while we often think of these materials being very volatile rich, the interiors are actually some of the most volatile pore materials on the moon. And while these features were well recognized in the Apollo era in terms of the exteriors of these glass beads being very rich in volatile rich condensates, it has to be said that most bulk processing techniques are influenced by several other phenomena. So in the sense of a large integrated signature in terms of grouping all these beads together and assuming they're all the same, as well as the fact that the vast majority of their volatile inventory exists on their exteriors and exist as coatings. So most bulk processing techniques are sensitive to these other phenomena. And if we look at more detail in terms of how the volcanic glass beads are distinct relative to the Mare basalts in both zinc and sulfur, zinc and chlorine isotope values here on the left and right, we see this effect of this reservoir effect where this condensate is dominating the signature we see in these rocks. Now, there's more nuances here in the sense that the interior zinc isotope values of these materials really has not been characterized quite yet. And we'll need large sample allocations to adequately constrain that because of the fact that most of the zinc's on the exterior of these glass beads. And to wrap up this kind of surface component problem here, I want to point out the fact that we looked at this too in terms of the effusive rocks as well. This rock here, 10017, is particularly odd. And in our work, we tried to isolate the exterior and interior of this rock. And if we look at both the chlorine and zinc isotope values of these interior and exterior chips, we see a lot of heterogeneity here. So these components we think are very superficial are not always on the surface, and often they're a bit more pervasive. And in terms of summarizing the Mare basalt suite and this for the volcanic rocks, I wanted to say that largely what we're seeing here is that much of these signatures are inherited, and while post-eruptive effects are clearly important, we need a real in-depth study on a sample-by-sample basis to characterize what is driving the variability here. So I think sample 10017 is really a really good analog to look at here to see what processes are changing and moving around these elements to better understand the broader story. Now, with that quickly out of the way, I really wanted to focus on primarily the Highlands rock suite today and impact processes. So this is what my primary focus is for this talk today. All right, so again, the Highlands rock suite represents early crust building processes and are the oldest rocks we have from the moon, but their petrogenesis is very complicated. And the impact history of the rocks also complicate the assertion that these rocks are recording some kind of primordial signature on the moon. We have two dominant rock suites, the Ferroan anorthosites and the magnesium suite. And if we focus specifically on their chlorine isotope values and chlorine contents here, all of these rocks are thought to be the most primitive primordial rocks and very important to understand crust building processes. They actually have the highest bulk rock chlorine isotope values of any planetary materials measured to date here, showing a real stark increase in chlorine content and isotope value in what is, to my understanding, the most well-dated rock on the moon, 60025. And if we look at, if we compare other stable isotope systems here as well, So comparing chlorine and zinc here, we see that the Highlands rocks show us the most wide ranges of chlorine and zinc isotope values in this case. And in the case of the fan specifically, we see a stark decoupling with high chlorine and zinc contents, but with very different isotope values, very high chlorine isotope values and very low zinc isotope values. And a few years ago, we asserted that this decoupling of values was related to how these fans were in place, where the flotation of a mushy cumulate pile of plagioclase during the final stages of magma ocean crystallization would be experiencing kind of the degassing, and that gas would be traveling through a permeable, mushy and acidic crust. And ultimately, our assertion here is to say that this process would relate to the deposition of highly evolved late-stage vapors from the final parts of lunar magma ocean crystallization. Now, this diagram here is how we modeled this, and I want to break this down here because I think it's very important. This is very similar to the Rayleigh degassing model I showed earlier, where the red line is showing us our residue starting from an initial source region composition of a certain fractionation factor. And the blue line is showing us the vapor component being lost from that system. And the idea here is that we think that as this mushy acidic crust cooled and became less permeable and colder and was able to deposit these volatile elements like chlorine and zinc, that the later it occurred kind of gives us a later starting point for deposition. So I want to key in on these 3 points A, B, and C and focus in on this black line here and target it as the integrated deposited vapor from these points. So these points kind of give us a starting point of saying, if the fan crust cooled at point A, B, and C, and we start collecting that vapor being driven off that residual magma, we can get both these really high isotope values and, more importantly, that relationship of high chlorine contents and isotope values at the same time. So our assertion is that the fans are recording this very late stage, possibly point C here in this case, integrated vapor deposition from a highly evolved, highly degassed lunar magma ocean. And really what I wanted to focus most on today and discuss what I've been working on a lot the past couple of years is kind of trying to better understand the confluence of impact processes on the crust building process. And many people who have worked on these rocks will recognize that they are very beat up. Many of the Highlands rocks are cataclastic. They are extensively impact processed. And the logical question that follows here is, what are the effects of the impact process on these rocks? And what is the influence of this process on the volatile inventory of impacted rocks broadly? So what we did here is we measured it. So here in this case of sample 60025, you're seeing the primary main mass of the rock in white with the impact melt coat on it in black here. Now, almost all the Highlands rocks are covered in impact melt, and their chemistries have been well constrained by Dick Morris and others in terms of mixing local protoliths. But we wanted to see whether or not the anomalous isotope value we measured in this rock on the interior was actually representative of the impact melt instead of the interior of the rock. So here on the right, I'm showing some unpublished data of the chlorine isotope values of the impact melt coats on some of the fans here. And I want to really key in specifically on 60025. And what we can see here is that if we look at the impact melt coat of 60025 relative to the interior of the rock, this is a separate component. The contribution of the impact melt cannot be attributed to the exotic stable isotope value of this rock. And this is a separate problem, a separate, very difficult problem to address. And that's what we'll be discussing going forward here. So again, the impact melt coat is sampling a different reservoir and is not the source of the very high 30 per mil value we see inside the rock itself.
What are the blue lines?
The blue lines are linking the structurally bound and water-soluble chloride isotope values of the fans.
And which is which?
They're all connected. So the blue lines
Which
connect.
is structurally bound and which is the water
The
soluble?
water-soluble is faded in this case. Thank you for the question, or the point there, yes. So for these rocks as well, we've also sampled separately the water-soluble and insoluble chloride in these rocks, giving us an idea of where this chlorine is going and how it's moving around. So anyways, yes, this is a separate problem that we've been digging a lot into the past couple of years. And to kind of explain the rationale for this here, I'm going to use halogen contents of impacted materials and impactors to kind of explain to you how I'm thinking about this and how I'm constraining this problem. So this plot is showing you the fluorine and chlorine contents of lunar protoliths, impacted materials, as well as impactor materials as well. This includes some hopefully soon to be out halogen data for chondrites this year, as well as some halogen data from a compilation from Jovanovic and Reed throughout the 70s and 80s. And what I want to pass across here primarily is that materials that are known to contain impactor components and are suspected to have been influenced by the impact process have very high fluorine-chlorine contents. And there's two options you could explain these data with. You could say that these volatile excesses are derived from an endogenous source, say the gassing and deposition of volcanic-derived gases, or it could be an exogenous source, say derived from the impactor component itself. And then on top of this problem too, you have the process of these are impacted, these are heated to very high temperatures. Are they also being isotopically fractionated from the impact process itself? So to break this question down, this problem down requires addressing two questions that I want to break down one step at a time. And that is, what is the contribution of impactor-derived volatiles? And how does impact processing affect volatile contents and the isotopic value of a given volatile element? And I spent a lot of time thinking about how to best articulate this, but we're going for this today. So to adequately address this question requires you to constrain what you gained to know what you lost and how you lost it. And what we're doing with this purpose is oxygen specifically. So triple oxygen isotopes allows us to constrain the impactor component and how much of it is inside a given impacted material. On the left here, I'm showing you what we call a little delta plot, showing the range of triple oxygen isotope values of planetary materials. And I really want to emphasize the enormous range that exists here in terms of the impactor components we could possibly look at. On the right, I'm showing you a big delta O17 plot here that is showing mixtures of these possible impactors. On the right, you'll see two horizontal bars, a range of mafic minerals and plagioclase minerals measured by Eric Cano. And I want to specify that this range in x-axis space simply represents protolith materials. So a protolith comprised entirely of iron magnesium silicates would be lower O18 values, and vice versa for a plagioclase-rich protolith. So this origin of these mixing curves in x-axis space could change depending on that space. And what I've done here is I've modeled mixtures of impactor types with a lunar protolith. And what each one of these lines represents is a 1% mixture of that impactor composition, whether it be an ordinary chondrite going vertically here with high big delta O17 values, or a carbonaceous CCAM-like impactor with low big delta O17 values. And also, if you mix a CI type material into it, very high increase in O18 values here. And I'm going to use this schematic to break down what we've constrained in terms of what impactor components exist in some of these materials to try to constrain the volatile contribution brought by that impactor. So we've worked on this a lot in terms of looking at impact melt coats first. So again, the impact melt coats exist on almost all the Highlands fan rocks. And if we look at their triple oxygen isotope values here, we see we have generally a high big delta O17 value. Now we will be able to constrain this better with a larger mixing model by constraining the major element chemistry to know where the protolith x-axis origin is here. But across the board, we're seeing a largely ordinary chondrite-like component added to these impact melt coats. And importantly, by constraining what we gained here, we can also say what contribution of volatiles were also brought alongside these impactor components measured in oxygen. And I modeled this here to try to address this contribution of impactor-derived volatiles. So on the left plot here, you're seeing a two-component mixture of an ordinary chondrite-like impactor. The bottom plot is showing you the change in big delta O17 value with increasing impactor Reynolds fraction. And the top plot is showing you the chlorine content that would be added to this material as impactor fraction increases as well. The gray bar, I wish I could point to this, it'd be a lot easier. The gray bar on the bottom is showing you the range of protoliths ranging from 1 to 10 ppm. So a protolith with no impactor component exists between this range. And as we add the impactor component we have identified via oxygen, we can see that the impact product range seen in the horizontal blue bar can be easily explained by adding this minor impactor component to it. So with this constraint, we can explain the chlorine content excess of the materials, but it doesn't quite explain the chlorine isotope value of the materials. So for that, I'm going to share some more data here that hopefully will be published pretty soon. And if we look at the chlorine isotope values and chlorine contents of possible impactors, whether it be ordinary chondrites in these teal squares or incident chondrites in the red triangles here, these materials exist upon a devolatilization curve. And we have a non-unique solution here in saying that, okay, we have identified the impactor component in oxygen. We've quantified how much volatiles that impactor would bring. But now the question is, the chlorine that was added to it, was it fractionated from inheritance or fractionated by the impact event itself? And what I want to key in here is saying that if we compare the impactor components relative to the impact melt coats here, we can see that these are distinct. So the fact that they don't match means that we have a fractionation occurring due to the impact process itself. And now for the next question we need to address here is, how does impact processing affect the volatile contents and the isotope values of the materials? I really enjoyed the papers from Housley discussing the impact processes that occur in regolith. And I think this simple cartoon kind of conveys this well in terms of we're dealing with a complicated problem of both adding material and losing it. And we really want to constrain every part of this to be able to know what's going on. So we have a non-unique solution of whether or not we have an inherited isotope value or a fractionated one for the impact process. And to better constrain this of how the impact process affects these volatile inventories is a surprisingly difficult question. And it's one I've been working a couple of years on now. And hopefully I've made some tangible progress on it. And for this, we need to explain what regolith is and how regolith plays into the broader story of the impact process. And on the right, I'm showing you an image of a nice fluffy regolith that is just this amazing little rock powder. And this material is made by extensive impact processing of lunar protoliths. So both solid crystalline rocks as well as the individual separated components within the regolith itself. On the left, you can see an image of what some of these individual components look like. And what these materials are the breakdown products and are further broken down to make the regolith itself. So to constrain the broader system here, we've done an in-depth analysis of these individual components to see what is actually moving and how it is moving around. So to give a little more detail as to what is in this primary components, we have primary protoliths and things like rock chips, volcanic glasses, primary minerals in the case of plagioclase, and we have impact products like impact glasses and agglutinates that represent the impact process being performed on the protolith material. And to make tangible progress on this problem, I've had to key in on a particular type of material to understand what's happening. So I think the best material to look at here are the lunar agglutinates. And these objects are immensely diverse, both in chemistries and textures. And many people would say that they're categorized a different way, but I think of them simply as a highly vesicular impact glass. And the agglutinates are particularly helpful because they are both the product made from an impact event, the acute single particle made from an impact event, but they also represent, and their abundance represents the time average exposure age of a given soil. So on the right, I'm showing you an image from the Lunar Source Book showing isobeso over FeO relative to agglutinate content. This isobeso over FeO simply refers to the abundance of nanophase iron in a material. So with increasing soil maturity, age, impact processing, we have an increase both in this metric of maturity as well as agglutinate content. So if we look at materials with a lot of agglutinates, we know that that material was made by both an impact process and it was from a soil that was rather mature. So this material will be very important for our story. And we've taken this material apart. So specifically during the ANGSA initiative, we've taken the components apart within 73002 to separate these components, whether it be the regolith and the individual things within it. And here I'm showing you the same big delta 017 plot here showing 73002 taken apart here. And I've measured almost everything in the sample. I've measured the immature fraction, the mature fraction, different size fractions, and individual things within it. And what we can see here is that we have a diversity of chondritic impactors within the agglutinated objects in the impact glass that is largely diluted in the bulk regolith present there. So what we're identifying is that we're identifying a CCAM-like impactor present in the individual impacted objects in the regolith. And this is consistent with trace element modeling by Mason-Newman showing that the excesses and citrophile elements are also related to a CM chondrite-like impactor. Now, the thing I want to follow from this is to say that often these mixing relationships of both regolith and impact melt coats relate to a volatile-free impactor component. And really, I think what this data shows here is or rather questions, is whether or not that impactor component also brought volatiles as well. So with this, we need to kind of answer what are the relative input and output fluxes from impact events. If we look at the chlorine contents isotope values of regolith from Apollo 16 and Apollo 17 here, the Apollo 17 regolith is that 73002 Angswick core. We can see that we're looking at this rather high chlorine content and high isotope value. And really the question kind of becomes, how much of the signature is from the impactor itself and how much of it is fractionated from the impact process? And if we look at the impactor compositions, we can see that the isotope values of 73002 does not match that of impactors and requires a further fractionation driven by the integrated impact processing of the regolith. And I think what we can generally say here is that we have a dynamic steady state system where a regolith is both gaining chlorine and losing chlorine and fractionating it based upon what it is losing it from. So the steady state system is characterized by the evaporation of the residual and or added chloride, basically mixing along the fractionation and mixing with more chondritic derived chlorine. And to kind of conclude this thought here, I want to convey that, again, earlier we said that a mature, highly impact process regolith has a high glutinate content. And thankfully, we're able to quantify this a little bit in saying that if we look at the halogen content of a bulk regolith, so here you're looking at fluorine, chlorine, bromine, and iodine contents relative to a glutinate content of a given soil. If soil maturation and impact processing resulted in a net volatile loss as opposed to some kind of buffering in the steady state system here, the glutinate content of a soil should be inversely proportional to the volatile content. And instead, these are largely independent relationships. A glutinate-rich mature soil is not showing any less volatile content than a immature glutinate-poor soil. So I think this is providing further evidence of the fact that you have a volatile buffering of meteoric addition to regolith while it's being impact processed. And with that said, just to quickly summarize what we covered today, in terms of zinc, sulfur, and chlorine isotope values of Mariga salts, I think we're largely seeing a broad scale inherited signature for lunar formation. And in terms of what is actually causing further fractionation, I think the explosively erupted volcanic glass beads are really a great specimen to look at in more detail in terms of what process is attributed to this fractionation. And we need further research, and hopefully this is part of the survey mission to kind of look in depth at these specific processes that are fractionating stable isotopes in the materials. In terms of Highlands rocks, these are recording exotic stable isotope values that are related to the last stages of magma ocean crystallization. And while the impact process is potentially related to their petrogenesis, we can't really relate them uniquely to their stable isotope values. And instead, when we look at impact products and constrain the impactor put within them, we can see that the isotopic values of impact products show that impactors contribute significantly to the volatile element inventory of the regolith. And we see that we have a dynamic steady state system between impactor-derived volatiles and impact-driven devolatilization, maintaining a high volatile content in the regolith, despite the fact that it's being continually impact processed. So with that said, there is an abundance of time for questions, and I'm happy to go over anything that anyone wants to do, and thank you for listening today.
Thank you, Tony. Tony, you should be able to just check there to see if there's any questions.
I can run the chat, I think.
Okay.
Any questions in the room?
Yes, I do.
Chip, what is your
This
question?
is Chip from the University of New Mexico. Could you go through, I want to discuss fans and the chlorine isotopic composition of fans. Because you do show a lot of systematics with regards to the chlorine abundance and the degree of chlorine isotope fractionation in those fans.
This is the slide you want? You want that one?
Yeah, it doesn't make any difference. I know what the observations are. But could you tell me what, in your model for the incorporation of chlorine and the preservation of chlorine, the fans, could you tell us, one, what is the source of the chlorine that's incorporated in the fans, and what is it incorporated in? And then the next step is during, all of these fans, as you mentioned, survived a lot of impact processes, not essentially the splatter, but just the impact of the lithology itself. How then is that chlorine isotopic composition preserved from the initial formation to what you're essentially measuring?
Let's see if I can get all those things. Yeah, so that's a great series of questions. So I'll begin with the source of chlorine, and I'll go back to this, I suppose. In that there's a significant mass problem that rears its ugly head in terms of achieving a very high isotope value. So if we look at this Rayleigh plot here, to achieve isotope values at 30 per mil, we're having extreme amounts of devolatilization occurring. And the question becomes, well, how much is left over, and how do you get the systematics of increased chlorine content and isotope value? So I think the source of this really has to be some kind of final dregs of magma ocean crystallization, whether that be creep or something else. I don't see any other evidence, any direct evidence for what reservoir that could be derived from, but a creep-like reservoir seems to be most logical in terms of where it's from. If it is a creep-like reservoir, it appears to have only brought chlorine and not anything else with it. And that's where I think it's most likely in. In terms of what phase it is in our paper, we discuss how chlorine cannot condense by itself. It needs some kind of reactant phase. So say if there's iron present there, I think it likely exists as an iron chloride phase. Given the fact that we have a high water-soluble chloride content, that'd be consistent with that idea. But there likely is some component of the mafic minerals as well present there. For many of these rocks, that can be highly variable from chip to chip, whether or not you have 1% mafic minerals in the rock relative to 10. So I couldn't quite say for that. What was the other two? How is it preserved? That's a really great question. The preservation of the exotic chlorine in the fans is certainly one that is of importance. And I guess I would say that if you look at the chemistries of impact melts broadly, they seem to generally match what the things they hit look like. And it seems hard to reconcile the fact that many impacted products are volatile rich, not volatile poor. So it seems like we have some kind of a difficult mass balance of it's difficult to lose things from these impact melts, and how they lose things seems to be a difficult question that hopefully I will key on in the future. So I guess I would say that it seems hard to lose volatiles from impact melt broadly, and it requires this repeated integrated signature of beating it repeatedly and repeatedly to really drive it to be odd. So how is it preserved? That's a question I'm working on.
Okay.
I have a question, Tony.
Yes, Zach.
You have a picture of the oxygen isotopes of the regolith, and they have a high delta 18 value and a constant delta 17, which you attribute to, I don't know, the CI or something?
CM, yeah.
Yeah. But that's not a big change in delta 18. Could it not just be a little bit of higher proportion of plage, for example?
Certainly.
Without any excess contribution? You mentioned siderophile, elevated siderophile. Is that actually what you see in those samples? So it does, because that would help you.
Yes. So to kind of unpack what all this means here is that when we first started the ANGSA mission, we were tasked with understanding the volatile history in regolith. And to do that makes you really carefully consider what is regolith, what is in it, and what is actually carrying the signature you're measuring. So in the case of oxygen, I think any given bulk regolith sample is just very much diluted relative to the impact products. So unless you actually isolate and individually measure the impact product, that material is diluted relative to the bulk regolith. So I think the bulk regolith is hard to identify that impact component because it is so dilute of a mixture. And in terms of the comparing the impactor component with siderophile elements, this is a difficult question. A lot of people think that nickel contents are almost entirely derived from impactor components themselves. So really my motivation and goal here is to try to combine these things, of combining lithophile and citrophile elements to get to a more robust impactor composition to see what is happening here. Because another critical facet here is that it is often asserted that agglutinates are formed during a extremely high energy process where you're evaporating silicates as well. So we're dealing with multiple different directions and processes here, and the dominant one appears to be impactor mixing more than anything else. So we're unpacking that one first. Hopefully I answered
If
your
you're
question.
mixing that with CM, your O17 should go down, right?
Correct. The CM is most like, this is CM basically.
Yeah, okay, so then the squares are either CIs or simply a higher pledge content.
Yeah.
It probably doesn't take much additional pledge to change your O18 value by 2/10.
Correct. And the idea with this is that if you were to measure the same exact impact melt for major elements in O17, you could constrain this very well. You can constrain all these processes. And that's ultimately our goal here and what we're working on currently. Karen Ziegler.
I'm not really 100% sure because you're saying there in your key, in your legend, you say CCAM, CC. CCAMs are a wide range of both delta routine and big delta 17. And if you're talking about CMs, being that one line, CMs have a fairly large range as well. So
I'm making a broad brush generalization, absolutely.
this is very broad.
So these 3 points on the CCAM line, I just picked basically at different points on it. So this is more like COs, this is more like CEs, this is more like CMs.
But look at what the COs are on the diagram to the left.
Absolutely. Yeah, it's absolutely fair criticism.
So you should either refer to specific meteorites or but then just labeling it CCAM, CC is not really correct in this, what you plot on your diagram.
I think that's
How about carbonaceous content?
that's more fair.
That's CCAM.
Yes.
That's the range.
Because it's a huge range, which your extrapolation on your plot doesn't really match. Anyway, that's a very specific oxygen isotope thing.
Yeah. With more unique solutions, we could better constrain this. As a first broad brush approach, we can identify carbonaceous like, and that's what I'm trying to argue more than specific type.
Any questions online?
Justin has his hand up.
Oh, I see hands up. Justin, please ask a question.
Yeah, thanks, Tony. I'm interested in this oxygen story, but I was actually, my question had to do with the plot of the chlorine, the impact versus the interior data. I don't know if it's forward or backwards at this point, but it was.
One where it said, what are the connecting lines, Tony?
Yeah, with the connecting lines, exactly, Zach.
I see. Okay, I got
I
you.
think it's towards the end, yeah.
Yeah, that works. And so, if I understood correctly, what you've done here is you've measured pairings between like the interior of a sample and one that has evidence of impact melt textures or material on the outside, and you found that there was a difference.
Correct.
And so, but you didn't attribute it to impactor, but actually process. Right. Yeah. Okay. And so then I guess my question has to do with, and maybe it's more than one process, and maybe that's the answer. But you have different directions. Sometimes you're almost always you're increasing the 37 delta value, but not always. And then sometimes you're decreasing the chlorine content, and sometimes you're increasing it. So do you have a process that does all that, or do you have a couple processes that can do that, or am I asking a reasonable question?
Yeah, no, I think it's reasonable, but I think it's a bit more nuanced than it's easy to appreciate, because the chemistries of the impact melt codes relate to mixtures of protoliths that also can be regolith as well. So any given impact process material, you have to assume that it both is representing an impact process that made it, but it also could be inheriting a previous impact process from the protolith itself. And that's where I think this is very nuanced in the sense of how do we look at the specific process in an isolated instance. And I think agglutinates are where that occurs then. The agglutinate gives you the acute impact process from the bulk regolith protolith.
Okay, so
Yeah.
Yeah, I didn't quite understand that when you were saying process. So let me just repeat my question if I understand what you're saying now, which is the process includes a mixture between the the target, regolith, and the impactor, and that
Correct.
mixture is part of the process when you say it's not the impactor. Okay, so there is a mass balance problem here too. It's not just the actual physicochemical process that's what I thought you meant by process. Okay.
Exactly. And I spent a lot of time last night really debating with myself whether or not to share the slide today, and the idea of the entire mass balance being driven by the evaporation of the additive component and the addition of that component. And I think there's a lot more nuance here. I'm sure other systems would disagree with me here. But in this kind of model, it would be to say that if you have a quantitative uptake and a fixed alpha of loss, I think it fit along this array of lines more or less. And I'm not about to say that all the chlorine in these rocks relates to impactors yet, but I think it's a critical part of the story of understanding why the materials that are so impact processed are volatile rich, not volatile poor. Hopefully I answered your question. If not, please keep asking it.
No, that was great. Thank you. And I understand that there's complexity that I didn't understand when I asked my question. Thank you.
There are no more hands, but if anyone wants to speak up and say something, that'd be great.
While you're waiting, I have another question.
Chip, please ask your question.
Yeah, you've shown two sets of data, one from the fans, one from the Mare basalts. The data from the fans suggest a degassing or devolatilization of the lunar magma ocean, whereas the Mare basalts indicate there's no degassing of the lunar magma ocean. Can you link those to a particular model, whether degassing is really occurring and when is it occurring?
Yeah, I think it's a great question. And I think it comes back to kind of what is the fundamental process driving the boat here? And in terms of how are you actually losing volatiles from a melt? And really, I go back to the basics of saying that to lose a volatile from a melt requires you to exsolve it and have that bubble be lost from the system. And in the case of when loss actually occurs, when that saturation occurs, seems to be extraordinarily late in the lunar magma ocean process of crystallization. That's simply not recorded in the Mare basalt source region, and only recorded in Ur creep or things that are these really small reservoirs relative to the bulk.
So again, perhaps you didn't analyze all the Mare basalt samples that you needed to, such as the creepy basalts, right?
Oh yes, there's most certainly more nuance to this question that I'm putting down here. I think this is a really critical facet to understand the moon's volatile history, because of the fact that we look at rocks that are extremely evolved and ones that are not very evolved, and try to link the two together. When in terms of what is actually causing the loss of volatiles may only occur at these extreme extensive crystallization that may only be represented in a few given rocks.
Great.
Any other questions from anyone online? All right, well, thank you everyone for coming, and feel free to send me an email if you have any questions or interest, and thanks for showing up.
Thank you very much, Tony. It was great. I just want to remind everybody online that next week is the last seminar that we'll be having before the Lunar and Planetary Science Conference, and then we'll pick up again the week after the Lunar and Planetary Science Conference. And next week's talk is going to really focus on the utilization of planetary surface materials for construction on planetary surfaces during human activities. Again, I want to thank you all for joining us, and we'll see you next week. Bye-bye.